Okay, Assalamualaikum, selamat pagi, good morning. Welcome back to SII1006. Surface processes. This is SII1002. Earth surface processes. This is lecture number 6. Apologies. In this course, we are covering sediments and sedimentary rocks. We've gone through the topics of looked at sediment classification, sediment definitions. We've looked at sediment textural properties, right? And also the concept of diagenesis and the process of lithification of sediments, turning sediments into sedimentary rock through the process of cementation and also compaction, right? In the most recent class, we looked at sediment transport and deposition, where you need to have an agent of transport, which is usually a fluid, right? And the most important agent of transport on our planet is water. Wind is also important. We can also have ice transporting sediment. We've looked at that. We've looked at the relationship between grain size and the velocity of the flow, the speed of your flow, right? Which can be demonstrated by the Hillstrom diagram, right? We've also looked at Stokes' law, right? Okay, so today let's have a look at the product of sediment transport and deposition, right? So when you have sediment interacting with an agent of transport, for example water, right, you start to get interesting geometries developing in your deposit, right? Okay, and these structures, these geometries here, we call them sedimentary structures. Okay. Okay, so I try to move my slide. Start. Okay. Okay, so what are sedimentary structures? These are structures created by erosion and deposition of especially clastic sediments that reflect the depositional conditions under which they were laid down. For example, you can get structures, things that we call things like bedding, cross bedding, ripple marks, fluid casts. They can form within beds, within your sedimentary deposit, on top of your sedimentary deposit, and also at the bottom of the bed. Okay, and they are very useful for helping us to determine the orientation of deformed beds. Right, you probably learn in other courses. You can have rocks which have been tectonically deformed, right? So you have folds and faults, and some beds, some layers can be overturned. So that's going to be a challenge for the geologist to decipher Earth history, because he or she needs to determine where to start the story, right? So you need to know which ones are the older beds, which ones are the younger beds, and in order to do that, you need to know the orientation of your beds, right? Are they overturned? Are they still in original position, and so on, right? So another use of sedimentary structures is that they tell you what kinds of processes occurred in the setting in which they were deposited. So they are very useful clues to the paleo environment during ancient times. Let's say if you find any desiccation cracks in your rocks which are 150 million years old, and you know that it was a relatively dry period during that time, and it was a continental setting, and there were animals living on the surface and so on, right? So let's have a look at the different types of sedimentary structures which can be preserved in the rock record. This is not an exhaustive list. There are too many different types of sedimentary structures, and I suspect there are still new kinds of sedimentary structures being described or discovered right now. Okay, but what we're going to do in today's lecture is just a very simple virtual tour of the most common types of sedimentary structures geologists will typically observe in the rock record. Okay, so things like beds, current generated sedimentary structures like ripples and cross beds, wave-formed sedimentary structures, surface marks, soil marks, and also soft sediment deformations. Okay, so let's have a look at these kinds of sedimentary structures. But I think the most basic kind of sedimentary structure that you need to know is what we call the bed. Okay, and what's a bed? It's a package of sediment arranged by the processes of sedimentation. Okay, it represents a single event of deposition, and you can distinguish individual beds by changes in the texture of a sediment within them. Okay, so what is a bed? It's basically just a layer of sediment deposit, right? So it's a layer. It has a thickness, has a top, it has a base. Okay, and it was deposited during a single event. So for example, you have, let's say you have a small lake here, and then you have a flood. Yeah, so that's an event, right? Or maybe a volcanic eruption or a landslide, those kinds of things, right? So we have an event, and let's say a flood in this case, and that flood lays down a single layer of sediment, right? And next year you have another flood, you get one more event, and this can repeat itself, you get lots and lots of layers, and the individual layers represent different events, right? And the different events might have different, they might have different degrees of energy. Some of them might be more energetic events, more cataclysmic. Some of them are more quiet events. So you get differences in textures between the different beds, right? Okay, so that's the definition of bedding. Okay, okay. So I have here some photos of beds, right? So this is from Labuan in the Federal Territory of Malaysia, but in Borneo. So here I have individual beds of sandstone, right? And they are less than 1 centimeter thick in this case. Right? That's a pen for scale, right? And these are maybe up to 5 centimeters thick at the top here. So each of these beds can be distinguished from each other. They have different textures. We have sharp boundaries between them, and they were deposited by at different times by separate events, right? So in this case, I have one water flow, one river flow. Next year, I have another river flow, and so on, for example. Right? But top photo also shows beds, but in this case, they have been tectonically deformed. So they are now oriented vertically. There's a vertical beds, right? Okay, so geologists for scale there. So again, each bed, individual bed, represents a single event. In this case, these are deep marine deposits. Each of these beds were deposited by what we call a turbidity current. Okay. So you know a bed, it's a deposit of a single event, and you can describe the properties of your bed. You can talk about the thickness of your beds, right? So this photo is a cross section of several beds, right? So you can measure the thickness of your beds. Just put a ruler here and just measure the thickness, right? You should note that a bed has a top and also at the base, okay, and also the horizontal surface of the top and the base here of the bed, we call it the bedding plane. So that horizontal plane, we call it the bedding plane, okay. And of course, principle of superposition tells us that if you have a succession of beds like this which has not been deformed, the older beds are at the bottom, and then it is overlain by successively younger beds at the top, right? That is common sense. That is the principle of superposition. Okay, so if you're in the field looking at rocks in the outcrop, right, you should describe the thickness of your beds. It might tell you something about the environment. Some photos here to show you the variations in thicknesses of beds. For example, here we have very thin beds here. They are millimeter in scale, right? Less than 1 centimeter thick, these layers here, right? Individual stripes here, right? Whenever you have these beds which are less than 1 centimeter thick, we usually call them laminae, right? So in this case, I can describe the sandstone here as a laminated sandstone, right? But yeah, beds proper will be 1 centimeter and thicker, right? So, for example, here we have, in this case, the beds are centimeter thick, less than 10 centimeters. So these are thin beds. Okay, thin beds in this. Or sometimes beds can be very thick. These are very thick beds. Notice the trees here for scale, right? So these beds are meters thick, right? So we call them very thick beds. Okay, you should describe the thickness of your beds. Another thing that you should describe is the external shape of the beds, the geometry basically, right? So, yeah, some beds can just form simple tabular beds, we say them, right? It's just horizontal with a straight top and straight bottom, right? So these are what we call tabular beds, very simple geometries. But not all beds look like this. We can have lots of geometries. Some can be wedge shaped or lensoidal, or maybe even have irregular shapes to them. Okay, so for example, here I have another photo from the field. This is from Bintulu in Sarawak. These are 20 million old marine deposits. Light color is sandstone, but dark gray color is shale in between. So here, notice I'm tracing a single bed here. That's the top of a bed, and that's the base of a single bed. And notice it pinches out towards the side, right? And to form these lens-shaped beds. So these are lensoidal beds, right? Okay, now these are actually storm deposits. 20 million years ago, there were storms in Sarawak. Okay. So another kind of sedimentary structure associated with beds that we usually see is what we call graded beds. Okay, this is graded bedding, where you have a systematic change in grain size from the base of a bed to the top of a bed. Okay, so for example, here are some photos. This is a single bed. This is the base of a bed, and this is the top of a bed. Okay, and notice the change in the grain size. Here you can see the spots here, right? So that is granule size. These are gravel sized grains, right? So this is a gravel at the bottom, and notice what happens as you move up section. It changes into a finer grain sediment. This is coarse grain sandstone and into a medium grain sandstone. So if you draw what we call a sedimentary log, looking at this grain size variation, this is what you get. This is a horizontal scale is grain size, the other went with grade scale, and this is vertical thickness, right? So see what happens. Grain size gradually decreases as you move up section. So this is called a normal graded bed. So this is the feature that we call normal grading. Okay, so another example of normal grading, a conglomerate in this case, lots of matrix, polysorted, relatively rounded grains here, you can see, right? And notice what happens as you move further upwards, it becomes finer and finer grain. So that's also normal grading. Okay, so in normal grading, you get an overall decrease in the grain size from the base to the top. Okay, and how do you produce normal grading? Well, we've learned about Stokes' law, right? So that can happen. So you can have lots of grains of different sizes, and for some reason, everything is dumped into the water. Everything is in suspension, right? And when the grains start to sink down, the grains with the largest diameters will fall down faster. So that's Stokes' law, right? So what happens is that you get an accumulation of the coarsest fractions at the bottom, and the grain size fraction becomes finer and finer as we move upwards in that section. Okay, so that's one way to produce a normal graded bed. Another way is, let's say you have a river flow, right, and you have fast flow, and during fast flow, only the coarsest grains can be falling down. But then as the flow winds get slower and slower, you start to get the finer grain particles falling down, being laid down, right? So you can get also, through a decrease in the flow strength through time, a normal graded bed. Okay. So yeah, that's a normal graded bed, but it doesn't have to be normal grading. You can also have the other way around, where you have inverse graded beds or reverse grading. Okay, so you can also have inverse grading, where there is an overall increase in grain size from the base to the top. Okay, so you go from, in this case, you have the sedimentary log. It goes from medium grain sand at the bottom, but the grain size gradually changes to coarse, to very coarse, to gravel as you move up section. Okay, so that is inverse grading or reverse grading. Okay, and these are examples of inverse grading or reverse grading. I have several beds. That's 1, 2, 3, 4. Several small laminae at the top here, right? So bed scale is, if you remember, put it there. That's going to be 1 centimeter. Right? So notice what happens here. You have dark colored shale. This is clay at the bottom here. It grades upwards into silt, and then I have a very thin, very fine sand layer at the top here. So that is reverse grading. Okay, so you go from fine to coarse as you move up section. How do you get these kinds of things? Well, you need to have a process where the energy of the flow becomes stronger and stronger and through time. Okay, so maybe there's a flood and it starts with normal conditions, right? Water moving very slowly, but then as the flow waxes, it gets stronger and stronger and stronger. You get coarser grains being transported to the area and starting to be deposited at the top. So you get a reverse graded or inverse graded bed. Okay, so beds. Beds are the most basic type of sedimentary structure that you need to know. Let's move on to what we call current generated sedimentary structures. So in this case, you need to have an agent of transport, water or wind, let's say, and they're moving in one particular direction. It's unidirectional, it's in one direction, okay? So this is a current, okay? So because of that current interacting with the bed of sediment, you can again get lots of different kinds of sedimentary structures. Okay, so these are current generated sedimentary structures formed from the transport and deposition of sediment by current flow of a fluid, water or air, and so on. So you can get things like ripple cross lamination, cross bedding, plane bedding. So let's have a look at these kinds of sedimentary structures. Okay, so this is cross lamination. Okay, or cross lamination, and these are associated, or you can interpret them as, and also give it a name like current ripple cross lamination, because they were formed by a current, right? So in this case, notice here I have several beds. They are centimeter in thickness. That's a single bed. They have a lensoidal shape to them, right? Not really tabular. Notice inside the individual beds here, let's say I focus here from, this is the base, this is the top. You have these inclined layers, right? And they are laminae scale, so we call them cross lamination. Okay, so you get these millimeter to centimeter thick beds, and they have cross lamination inside them. And what are cross laminae? They are thin inclined layers of sand which build up to form the sedimentary structure called cross lamination. Okay, so individual beds, like I said, they may be tabular, maybe have undulating tops. They also may be lensoidal in shape. So these are what we call ripple cross laminated sandstones, and they were formed because there was a current flowing during that time. Okay, so that is ripple current cross lamination. When you go to the field and you look at the feature in 3 dimensions, you see there is a 3D shape to them. There's a certain 3D geometry to them. There's a certain bed form, we say, to the deposit, right? So in cross section, you might see the cross lamination here, but on the bedding plane, you see these features here that we call ripples. Okay, and you've seen current ripples before, right? You've probably seen them on, in shallow streams. You see them forming on the bed, right? See ripples. Or maybe you're on the beach and you can also see ripples. You can see a crest, right? And then you have a gentler side and also a steeper slope, right? So the gentle slope is called the stoss, which is up current, and the lee, which is the steeper slope, it is the down current surface, right? And then you have the ripple crest forming the hinge between these two surfaces, right? And in cross section, you go to, and what you see in the ripples is the cross lamination, and the cross lamination are always dipping down current. So it tells you the direction of your flow, right? Okay, so here we have ripples, and internally you can get ripple cross lamination. Okay, so you can describe the length of the ripple, the crest, the stoss, the lee, and the presence of cross lamination inside them, right? But how do you get ripples? Well, like I said, you need to have a current flow moving in one direction. Let's say in this case we have a shallow stream. Water is moving from the left to the right? So, so because of the water, and you get sediment transport, so you get all these grains. They are migrating. If we learn about the grains are being rolling, sliding, and some of them also saltating, jumping, right? So they're moving with the current. So they form these mounds of thin mounds of sand here, right? Okay, so on this side you get sediment transport and erosion. You get the stoss, the gentle stoss being developed here, right? And then the grains will accumulate on the crest, and eventually they will fall down to form this slope that we call the lee, right? And these ripples are moving, migrating towards the right. So you get sediments accumulating, you get layers and layers and layers which are inclined. So you're forming your cross lamination. Okay, but at the front here, as the flow passes the ripple, it meets with the sediments at the front here. You get erosion. Okay, at the front here. Okay, so you get a scour here. But then at the front here, you get more ripples being forming, and you form a train of ripples which are moving and moving down current, and that's why you get cross lamination inside your ripples, right? So yeah, as a ripple migrates downstream, as sand is added to the crest, and it creeps on the lee slope. The crest and trough here move downstream too. The scour in the trough supplies sand, which moves up the stoss side of the next ripple here. And you get a whole train of ripple troughs and crests advancing downstream. Okay, sand that avalanches on the lee slope during migration forms a series of layers at the angle of the slope, and that's how you get cross lamination. So in this case, notice the dip direction of this cross laminate is towards my left. It's going towards the left. So we know that the water was moving from the right to the left. Maybe these rocks are, let's say, 50 million years old. So notice how we can tell a story from that. We can say that 50 million years ago, water was moving from the right to the left. Okay, so that's how we interpret Earth history using sedimentary structures. So example, I have a nice photo here. My geologist friend here. This is a photo of, near to the border between Sarawak and Brunei, Darussalam. This is in Lawas, right? So we have a sandstone bed here. The beds have been tilted, dipping something like 35 degrees, right? By tectonic forces, you have tectonic compression, so you have a fold being formed. And these rocks have fossils which are 20 million years old. This is from the Miocene. Okay, so what we are looking at here is the top bedding plane of a sandstone bed. Okay, and notice here you can actually see ripples. All these are current ripples. Okay, so that's the crest. I followed. Notice the crest is not straight in this case; it's undulating. And you have a gentler side, which is on this side here, downslope, and a much steeper side. This is the lee, right? So the lee is always pointing towards down current. So you can say 20 million years ago, there was water here. This was underwater. Lawas was underwater, and you had a current which is moving from in this direction and to that direction. Okay, so that's how, yeah, so ripples are very useful as what we call paleocurrent indicators. Okay, all right, so those are current ripples. Okay, but you can also have features which are similar, but they are bigger, they're much larger, they're thicker. So these look like cross laminae. You have these inclined layers within a bed. So this is one bed from here to here, a sharp surface, another bed from here to here, and another bed here, right? So these are beds of medium grain sandstone. Okay, so you get these inclined layers, but we don't call them cross laminae, we call them cross beds, because the beds, these beds here with the internal cross beds here, they are decimeter to meter thick. They are more than 30 centimeters thick, right? And how what's the maximum thickness? Oh, they can be hundreds of meters thick sometimes. You got these large dunes in deserts, right? So they can have cross bedding also, and they can be what, tens of meters thick. Maybe on Mars they can be hundreds of meters thick. Okay, so you get these kinds of features that we call cross bedding. Okay, they are just larger scale. Okay, these are cross beds formed in an aeolian environment, a desert environment. But these rocks are something like 200, if I remember, these are something like 225 million years old from the Triassic. Okay, so these are cross beds in cross section, and this is how they look like. You can actually distinguish two types of cross bedding. One what we call tabular cross bedding, where the bounding surfaces, the bottom and the top of a bed, they are relatively straight. Okay, so this is tabular cross bedding. And then you can also have what we call trough cross bedding, okay, where the lower surface is actually curving, usually in concave upward geometry to them. Okay, so this is trough cross bedding with curving bounding surfaces. Okay, if I move further, okay, so cross bedding is the internal structure of this bed forms, so it's 3D bed forms again, that we call dunes, right? So cross lamination is the internal structure of ripples. Cross bedding is the internal structure of dunes. Okay. What are dunes? They are very similar in shape to ripples, but they are just larger. That's the main thing, right? So you can have a stoss, you can have a lee, and you can have a dune crest and so on, right? But these are thicker and much larger. Okay. So what people have seen is that if you have tabular cross beds, it tells you that the crest of the dunes are usually straight, and you have trough cross bedding. You have dunes with more sinuous crests. Okay. So how do you get the formation of dunes? Is very similar to the same is the same kind of process when you to form ripples, right? So you have unidirectional current, and you have build-up of sediment, and then avalanching of the sediment to form the lee, and the lee side builds up with more and more layers of cross-bedding forming, right? And then you can have the erosion of the trough here, resulting in migration of dunes down current, right? So it's the same thing. You can have subaqueous dunes forming in rivers or in tidal straits or in deserts, right? Lots of different environments, as long as you have flow in a single direction. Okay, so yeah, just show you examples of modern day dunes and with cross beds. This is this is from a well-known publication from a tidal flat in Newfoundland, I believe. And so here, the geologists here, you can actually see dunes, right? And this is the stoss, this is the dune crest, and then you have the lee slope here. The current, in this case, the tidal current is moving from the right to the left. Okay, and then the sedimentologist here makes a cross section here using a shovel, digs here into one of these dunes, makes a trench, and this is what they found. You can actually see cross bedding, right? So we know, inside dunes we have cross bedding, right? And they form because you have flow in one direction. Okay. So just remember, ripples are smaller than dunes. Ripples are made up of millimeter to centimeter thick cross-laminated beds, while dunes are much bigger things, and they're made up of decimeter to meter thick cross beds. Okay. If you're interested to know more about the processes, you're welcome to go to you're gonna have to take my class next year on sedimentology, right? SII1004. Okay, so other beds formed by currents. When you make a cross section, this is what you get. There's lots and lots of parallel stripes here, parallel layers, right? So this is parallel lamination, or some people call planar lamination, right? They are associated with these bed forms, that we call plane beds or flat beds. Why? Because they're just a flat layer with a flat surface at the top, flat surface at the bottom. But when you make a cross section, you see they're made up of horizontal lamination. Okay. These kinds of sedimentary structures can also be formed by flowing water or any other medium of transport in one direction. Okay. You can find these in very fine to coarse grain sand. Laminae are very thin, 5 to 20 grains thick only. And sometimes if you look at the top bedding plane, you can see these elongate ridges. Just a few grain diameters high, separated by furrows, and these are oriented parallel to the flow direction. So it tells you the direction of the current. For example, here the current was probably moving from here to here, also in the opposite direction. So we cannot really determine the exact direction in this case, because there's no such feature like a Stoss or a Lee, right? Okay, and these are usually indicative of high velocity current flows, much faster compared to the flow that produced your dunes and your ripples. Okay. Alright, so those are current generated sedimentary structures. You can also have sedimentary structures developed through the process of waves. Everybody knows waves, right? You've been to the beach before and you get this movement of water, right? They form a sinusoidal wave. And if you, let's say you sit down and in the shallow waters of the beach, you notice that what happens is that you're not really moving that much, you're just moving back and forth, like this, right? Swinging back and forth. This is because the water, if you can imagine the movement of the water particles, they're moving in an oscillatory motion, like in circles like this. Okay, so the net direction will be back and forth like that. Okay, so because water is moving back and forth, right, the net direction is back and forth, sediment on the beach will be swept back and forth like this. And you notice the waves are just hitting the beach continuously throughout the whole day, right? There's a lot of cycles. So what you get is the back and forth sweeping of the sediment. So what you get is also a ripple, but the ripple is a little bit, in this case, the ripple does not have a distinct Stoss and a Lee. Both the right and left hand side of this ripple here, the angle of the slope is roughly the same, right? So the geometry is symmetrical. So we call them symmetrical ripples. Okay, and this is usually indicative that you had waves in your environment, right? So if you have an asymmetrical ripple, it's a current generated ripple, right? Like a river. So if it is symmetrical, probably associated with a shallow sea or a beach, right? Okay, so wave ripples are generated by waves in shallow water. They have a symmetrical profile or swollen lenticular profile. Okay, so these are ripples in sandstone, and they have a symmetrical shape to them. Okay, and they were formed by waves. Okay. Other things, surface features. These are markings that you can see on the bedding plane, on the top bedding plane of your bed. So for example here, these are footprints of dinosaurs on top of a mudstone. Right, so those are surface features. These are desiccation cracks in an arid environment, right? And those are also surface features. But let's have a look at desiccation cracks first. You've seen this before. You know, you've probably seen a dried up pond, right? After the rains, a dried up pond, and you see a mud layer at the bottom, and you see lots of these cracks here, right? What has happened? Well, the clay, the mud was saturated with water, but then you had desiccation, evaporation of the water, drying up. What happens is that the mud starts to shrink, right? It starts to shrink, and what happens? They shrink, and it cracks. So you get these desiccation cracks. Okay. Okay. In cross section, this is how a desiccation will look like. That's the crack, and they tend to taper downward, getting smaller and smaller, getting narrower and narrower, right? That's in cross section. Okay, these are desiccation cracks also. Notice these cracks, they have been infilled by younger sediment, so they're no longer empty space. They have been filled in by the overlying sediment here, and these are these darker colored layers. These are beds of mud. Okay, so these are interpreted as desiccation cracks, but these are old ones. These are Jurassic desiccation cracks. Okay, so now that during the Jurassic period, at this time, you had periods. This was a continental environment on land, and then you had periods of drying up, right, of the sediment. Right, so desiccation cracks. Okay. These are modern day desiccation cracks, and these are ancient ones. Again, from the Jurassic here, if I remember. So notice what happens. The cracks are no longer empty. They have been filled in by overlying sandstone, right? So you get these kinds of casts of of the original desiccation cracks. Yeah, right. In cross section also, the upper edges may roll up if all the moisture in the mud is driven off. Desiccation cracks most clearly preserved in sedimentary rocks when cracks are filled with silt or sand, washed in by water or blown in by wind. The presence of desiccation cracks is a very reliable indicator of exposure of the sediment to subaerial conditions. So let's say we've seen these kinds of desiccation cracks. For example, if you go to the area of Jerantut in Pahang, right? So there we have sandstones and mudstones, and we have plant fossils inside them, also dinosaur fossils inside them, and they are Cretaceous in age, right? Something like 110 million years old. And we found desiccation cracks there, so we know that everything fits. You have dinosaurs, you have plant fossils, and then you have desiccation cracks. So it must have been on land during that time, 110 million years ago. Okay, so we use those as clues to interpret the deposition environment. So those are surface marks. You can also have marks forming at the base of your bed. These are scour marks or sole marks. Okay? So you have the general term we call them as sole marks. Okay, and you have different kinds of sole marks. These are scour marks, for example, right? Don't worry, we're just going to cover just the basic ones. Go to more detail in second year. So an example of a scour mark is a flute cast. Okay, flute casts are erosional scours formed by turbulent eddies in a flow. Okay, so this is a cross section of a flute cast. You also have a bed here, which is made up of mud, right? And then you have a flow moving from the left to the right. Okay, so then you start to get turbulent eddies because of the irregularities of the surface here. And what you get in cross section is this: you have one steep edge opposite to a more tapering edge here. So the deeper part here is up current, and the more tapering edge is down current. Okay, that's what happens. In plain view, this is how it looks like. It has a fluted shape to it, right? You played a recorder before, right? And the hole looks like this, right? So it has a fluted shape to it, right? So in plain view, the narrower end is down current, and then it widens. The wider end here is down current. This is up current. This is down current. Okay. So what are these cartoons on the right hand side showing? This is just to show you. These are basically streamlines showing you the eddies, turbulent eddies forming within your flute cast in this case. Okay. So these are formed by moving water in one direction. These are current generated sedimentary structures, but they form at the base of the bed, not at the top. Okay. So originally they were scours, erosional features, right? But then imagine later on, sand is dumped on top of it, right? And then more and more sediment is overlying it, so it gets compacted and cemented. It turns into a sedimentary rock, and then all this is exposed, right? And then the softer mud below here is eroded, so you're just left with a cast of the erosional scours here. Tinggal acuan, okay? So that cast, that's called the flute cast. Okay, so in this case, these are flute casts at the base of a sandstone. This is from Kampung Pokok Sena in Kedah, right? In Kedah, and these rocks are Triassic in age, something like 230 million years old. Okay, so you need to have running water. So we say that 230 million years ago in Pokok Sena, Kedah, it was underwater in relatively deep waters. That's how we tell these kinds of stories. Excuse me. Now, these kinds of flute casts, they are very important indicators of the direction of the current, important paleocurrent indicators in the past. So, excuse me, I need some water. I might get dry. Excuse me. Okay, so this is a zoom in of the outcrop at Kampung Pokok Sena in Kedah. 200, something like 230 million years old from the Triassic. It was deposited underwater in relative deep water. You actually see some nice marine fossils associated with these beds here. Things like ammonoids and bivalves, right? So we can even determine in which direction the water was moving 230 million years ago. So remember, the tapering part is down current, is up current. Sorry, I'm always getting that confused. And the widening part of the fluid cast is down current, right? So in this case, the flow was moving from the right to the left. Okay. Other kinds of soil marks you can get. These are what we call tool marks. So in this case, it's not just turbulent eddies. You need to have an object forming the mark. Okay. These are marks created by an object being carried in the flow over a bed. So for example, let's imagine you have a riverbed, right? And then there's lots of there's lots of debris inside your river, and you can have a log from a tree, right, or a twig, and it touches the riverbed, and it's being dragged by the river current. Maybe it's a flood, right? So what happens? You get this nice straight line to it, right? You have this nice straight line to it, and later on, that bed is usually a mud. Later on, more sand is going to be overlying it, right? And then it lithifies, and the mud is eroded. You're left with a cast again. So this is what is called a groove cast. Okay, sharply defined, elongate marks created by an object being dragged along the bed. Okay, sometimes if you are lucky, you can even actually see what produced the groove cast. You just follow the groove cast, and then probably a fossil at the front here, which has been dragged. Sometimes, okay. You can also have things that we call things like chevrons formed when sediments are still soft. Then prod, skip, and bounce mark, where you have saltating objects, things which are jumping in the water, right? And they land eventually, so you get these these markings on the surface there, right? So these are prod, skip, and bounce marks. Just several holes here, original holes here. Okay. So these are tool marks. Okay. Okay, so we've looked at soil marks and also surface structures, and also tool marks, right? This is another kind of sedimentary structure. I believe you've already learned about things like folds and faults, right? Okay, and in mapping course, first year of mapping course, and we usually interpret these as the product of tectonic deformation, right? So you can have things like compressional tectonics, maybe continents are colliding and so on. So you can have the formation of synclines and anticlines, folds, right? But folds and other kinds of deformations can also occur without the process of tectonic deformation, just by simple processes of sediment deposition. Okay. But they need to happen when the sediment is still soft, has not been lithified, all right? Okay, we say that it is syn-depositional while it is still being deposited, or post-depositional, just directly after it has been deposited, okay? So we call them collectively soft sediment deformation structures, right? So they have to be soft sediment, not lithified sedimentary rock. So for example here, this is convolute lamination, right? So you have layers of sediment. Notice the top here. It's a nice tabular bed, right? But the layers below, they are folded, right? This is convolute lamination. Small scale folding of the layers here, we call it convolute lamination or convolute bedding, okay? So you can imagine how does that occur? Well, you need to have some kind of disturbance. The sediment was still soft, okay? Let's say you have thin layers of rippled sand, deposit, and it has lots of porosity, so the pores are filled in with water, they're saturated with water. Then let's imagine some kind of shaking. Maybe it's an earthquake, okay, or maybe it's just a whale passing through, just splashing its tail onto the seafloor. But let's stick with an earthquake, right? So it shakes, so the grains will rearrange themselves, and the pore shapes and the pore size will decrease. So water tries to escape outwards. So what happens? The layers become deformed because of all that movement, right? So that is convolute bedding or convolute lamination. Okay. Then there's also what we call load structures and also flame structures. So what are those? Okay, let's say you are near to a river mouth, okay, near to a river, but underwater, in the shallow sea, right? And there is a layer of mud below, right? And the mud is very soft because it has just been deposited. Lots of water inside it, right? It's very soft mud. If you can imagine, if you're stepping on the mud, you will sink. Okay, so it's very soft mud. But then, let's say you have a storm, and the storm brings with it a lot of sand, and the sand is laid down on top of that soft mud. What happens? You have clay below, and you have the mineral quartz, SiO2 above, which is much denser. So you have what is called a reverse density gradient. Everything's not in balance. So the situation needs to balance itself. What happens is that the sand starts to sink. Okay, and when it starts to sink, you form these bulges, which are pointing downwards, right? And these bulges pointing downwards, this can be later on lithified by the process of diagenesis, and then these older muds here will be eroded, and you're just left with this impression here. These are what we call load casts, and the structures are called load structures. Okay. But in between your load casts and your load structures here, you have this pinching out of the underlying mud. You know, as the sand and mud try to form an equilibrium, try to balance out, you get these flame-like structures in between. Just the mud needs to go up, the sand goes down to get a balance, right? So these are called flame structures. Why? Because they have a flame shape to them. Okay. Sometimes the load casts, they sink so deep they detach from the original bed. Okay, so you get these ball or pillow-shaped structures. So we call them ball and pillow structures. All right. So here are some field examples of load structures, flame structures, and ball and pillow structures. These are loads here and here. These are photos from Labuan again, 20 million year old sandstones. Really nicely preserved load casts and ball and pillow structures. Okay. These are smaller scale load casts and flame structures. This is pencil for scale, 13 centimeters. Associated with rocks which are Triassic in age, 230 million years old, near Jerantut, near Kota Gelangi. Yeah. Tells you that there was probably near to a delta, a river mouth. It was underwater. There was a lot of sediment saturated with water, high sedimentation rates, and you get sinking more recently deposited sand into the very soft substrate below. Okay. You can also have these large-scale folds being preserved. Right. For example, here, this is an outcrop. This is an outcrop near Mentakap in Pahang. Humans for scale during the second year field trip for sedimentology. You can see the anticline here. Right. So that's the axis of your fold. Right. And it's somewhat overturned here, right? Okay. These are not tectonic folds. These are soft sediment deformation folds. Okay. They did not form because of tectonic compression. You just had a slope failure. So these are marine deposits. You had this continental slope, and because the sediment was still soft, they slid down that slope and they deformed into folds. All right. So these kinds of folds, we call them slump folds. Okay, and the beds are slumped beds. Okay. So you get these folded layers, but they are not tectonically formed. We call them slumps. Okay. And then you start to ask, how do you determine whether or not it's the folds are tectonic or depositional in nature? Well, you need to have a look at the association with the overlying and underlying beds. Let's say if you have beds above the fold, which have not been deformed, and the beds below the fold are also not deformed, the deformation is just in the middle interval. That means that the folds are localized during a certain time interval, and those are slumps. Okay, if they were tectonics, they will basically just deform all of the beds, and they are regional in nature. Okay, this is an outcrop of a muddy slump Again, in Labuan, I always talk about Labuan because you have Labuan is a very nice place to visit. As a geologist, you have all the examples of different environments there, variety of sedimentary structures preserved. Yeah. Okay, so just another example from Bintulu in Sarawak. So I have a sandstone bed here. And when I zoom in into the sandstone bed, I can see I have marks along the base of the bed here, and these are lode casts with flame structures in between. Right. And when I zoom in inside the bed, I see a lot of convolute lamination, and also these dish-shaped structures here. Right. They have a smiley concave upward shape to them, right, inside the sandstone. And these will cause because water is trying to escape out of the sand layers, right? So you get these kinds of shapes to them. Again, tells you that there was some kind of disturbance to the still soft sediment during that time. Maybe an earthquake, or maybe a storm, and those kinds of things. Okay. Okay, so that's my virtual tour. The most common types of sedimentary structures you can observe in the rock record. Now, we go back to the reason that we want to know all these things, right? Why do we need to know sedimentary structures and their features? One, it helps us in deciphering the history of the Earth, what happened millions of years ago. It tells us what kind of setting, what kind of environment was it? Was it underwater? Was it continental? Was it in the desert? And what kind of energies did we have here? Was it fast, energetic flows, or just a calm pond, and so on, right? So we can determine this, but just looking at these sedimentary structures, we can provide supporting evidence for the interpretation, right? But in order to tell a story, your sandstone, mudstone, your layers, your beds, right? They are stacked on top of each other. You can read them like a book, right? So page 1, this happened, page 2, this happened, and so on. But in order to do that, you need to know where to start. Which one is the first page, right? So a book is easy, right? You have the pages marked, and everything's just nice, straight sheets, right? Horizontal. But let's say what happens if a book looks like this, crumpled up with no page numbers, right? How do you determine where to start your story? Do I want to tell the story like this? In the beginning, it was this, followed by this page, this page, this page. Or maybe it's in this direction. In the beginning, it was this, followed by this, by this, by this. Right? Because all these beds have been deformed. They have been tectonically deformed. They might already have been like this, but then because of compression, they are folded, become steep beds like this. In some cases, very deformed. They can even be overturned. Right? So you need to know what we call the younging direction. Okay. In which way does the sedimentary succession young? Okay. So, sedimentary bedding can be deformed by tectonics. How do we determine which beds were originally on top or originally at the bottom? So, this question is important. In order to unravel Earth history, we need to know which bed is older and which bed is younger. So, we use what we call younging direction indicators, or some geologists call it the way up indicators, right? So, certain sedimentary structures are very good younging direction indicators. For example, ripples. Ripples, when they form, the crest will always point upwards. Right? You don't have crest pointing downwards. So, you can use them as younging direction indicators. So, example here, I have an outcrop. One is overturned, one is not. So, which one is still in original position? This one is still in original position because the crest is pointing upwards. Okay. So if you have overturned beds like this and you want to tell a story, so notice you're going to be wrong because you're going to start here. In the beginning, this layer followed by this, but that's wrong, right? So that's why you need to know the younging direction. Okay. Cross beds are also very useful. Most of the times, the dip angle of the cross bed facet we saw, these layers here, the inner layers becomes gentler towards the base of the bed like this. Okay, they're more concave upward. And that's a good younging direction indicator, right? So for example, here again, 2 outcrops, one is overturned, this one is still in original position because notice here it's steeper here, it's getting gentler, moving down section, okay? And these are overturned, so you need to be careful. in using this to tell a story about the history of the Earth. You need to begin from here, then move here. Okay. Soil marks are always at the base of the bed. So if you have flute casts, they're going to be at the base of the bed. Okay. So in this case, you have overturned beds because the soil marks here are at the top right now, right? But they have been overturned because of tectonics, right? And also load structures, they sink downwards, they bulge downwards. So you can use that as a Young indirection indicator. Okay. So example, two outcrops again. So this one is the incorrect orientation because the flame structures are pointing upwards and the loads are moving downwards, are bulging downwards. Okay. Okay, so I'll stop there. Thank you for listening. Okay. Thank you. Bye.